I'm going to talk today about some work we've been doing at Swansea on array modelling and how that might work. This is part of a wider effort that we're doing, and I could also talk about some of our large-scale work and some of our blade element activity, but talk to me afterwards if you're interested in that, and just recognise my RAs and co-researchers. So we have a methodology. The Manchester group, wherever Peter is, glossed over this very quickly. Some of their results are following a similar sort of approach. It's a blade element model embedded within a CFD approach, which gives us a fast method for turbine modelling. The problem with that method in its basic implementation is it overpredicts power coefficient. And so last year at this assembly, I presented some work with some improved corrections. That's gone to renewable energy and it's still in press. So unfortunately, can't see what that is still a year on, unfortunately. If you're reviewing that, please get on with it. But the corrections we have allow us to give accurate solutions to both low and high turbulence corrections against the IFREMER turbine paper, which shows significantly reduced performance in high turbulence. I'm going to talk today about some comparisons between this approach and shallow water, and also some power shedding algorithms. Okay, so it's a standard RANS CFD model, where the rotor geometry is represented by a source term distributed over a disk. Within that source term, we have the twist called lift and drag parameters, so we can pick both a blade shape and a turbine design. And that gives us accurate power and thrust in the downstream wake. It's a fast computational speed compared to blade resolved or RANS type models, LES type models, and we can also model into that the support structures. So this is some work we're doing at the moment. This is a preliminary model of a floating device with floats either side of the rotor, which might look a bit like a machine that's out in the water somewhere near the Isle of Wight. So we're just looking at that approach there. The way it works is you're at your standard Navier-Stokes equation and you add a source term, and you can see that these source terms look like the blade element equations because they are, and they have a lift term, a drag term, chord and twist angle in there as well. Okay, so firstly to looking at wakes, the bottom left picture is from IFREMER. It's a profile from just behind the rotor, so the rotor is just off the front edge of that plot, and that shows their wake behind the rotor in the IFREMER test. And above that is our computational model. That shows all the same features and is quite nice, and in particular this increasing drop in velocity as you go slightly downstream in the centre of the rear of the rotor. You get some pressure recovery, which drops the velocity slightly further. The top right picture is a slightly zoomed out version of the same thing. So we're pretty happy that we can now match power, thrust and weight characteristics with this approach without the complexities of having to mesh a blade and a geometry. So it's quite nice. So we've done some work, and this is motivated by something that came out of Oxford. And Scott Draper did some of this work looking at a very simple idealised headland with a fence of some description offshore from that headland. And we've modelled this in two different approaches, both a coastal model using shallow water equations using the Mike code, and also within the blade element CFD model. And we've got to recognise some input from the Terawatt project for some of the resources behind this work as well. So the mesh for the coastal model is on the left-hand side. This is a subsection of the model for the coastal approach. It's actually 7,000 by 770 metres. We've had to build it larger because on the coastal model we're having to drive this with a tidal height change at the boundaries. So we need a bit of space either side to get that working correctly. So it's a standard coastal model, and we have embedded actuated discs in that approach like any normal shallow water resource model. The rotors are smaller than one cell, so we're already at quite a level of abstraction, which is the problem that coastal models have. And we run it transient and we run it with a variable surface height. Plot B and the zoom in plot C is the blade element mesh. It's 900 by 700 metres, which is quite a big model for a CFD model. It's quite a large scale. And we're using our blade element discs that I've just showed you. Within the rotor, we have about 50 cells across the diameter of the rotor. And we have some cells through the thickness of the rotor box. And what you end up with is about 50,000 cells in the rotor. And these are finite volume, linear, cell-centered elements. But that gives us the representation. If I go back to there, so there's your typical, the disk there is the elements that contain the source term. And there's about 50,000 of those in a rotor, and that gives us good, nice parameters in the downstream. You get variation across the disk in terms of velocities, etc. We've run this in a steady state approach. We can use these models in transient form, but at the moment we're still learning more about what's going on simply with steady state wakes. So we don't need to go to variable with that one, and it has a fixed lid approach. So these are the two models. And what you end up with is this. So on the left you have a blade element CFD approach, 50,000 cells per rotor, 6 rotors in our array. If you look firstly at the bulk flow, we get acceleration into the headland and we get a recirculation region behind that headland, and then you have the rotors themselves and the wakes. Because the flow curves around the headland, you get curved wakes, which is interesting for those of us that look at wake plots that are straight. We all think about wakes going up behind a turbine, and in this particular case they don't. On the right-hand side, we've got shallow water equations. We've still got 6 rotors in here, but each one is smaller than a grid cell, and so there's a level of abstraction. You can still see the same general approach. This plot is a velocity difference. So this is shallow water minus blade element, and you can see what's going on. And the lower plot is simply a zoom in. And what happens is, because you've got less elements, the shallow water equations, they underpredict the bypass. So we have an underprediction of flow going around. So in this region, just around the edges of the array, we get an underprediction in the flows there. And also we don't see quite as much wake deficit as we do in the blade element approach, which is interesting. There's a massive proviso here that as soon as you add turbulence and waves and bathymetry, all these lovely wakes dissipate. So whether we're trying to get wakes right or not is a slightly arbitrary when you go out into the real world, which we've seen in some of the other work we've published this year. Okay, some work we've gone on from that is we've started looking at power shedding. So all the work we've done so far has been looking at rotors at optimum CSR, optimum power takeoff. But we know in the real world that we limit peak power for economic reasons, and so rotors often run at less than peak power. Because of the model that we've got, the energy, which is energy extracted depending on pitch and velocity and rotational speed, because we just have a source term, we can control those parameters. So we implement a control model, which gives us 2 advantages over the basic one. Firstly, we can now automate our operation at peak tip speed ratio, which is quite nice, because what we haven't told you is some of our older models, there's an awful lot of guesswork, particularly if you look at this plot here on the left. Actually knowing what the inlet velocity is to the rotors is quite difficult before you run it. And so knowing how to set the rotor rotational speed to give you something that's running at optimum, it's actually quite tricky. And so a lot of the work we've done recently has been to try and take away that complexity. So what we can do now, we can just say we want to run at TSR4, and the rotors now self-control to the right speed, which is nice. That takes some of the guesswork out. That's also useful in arrays with variable inlet velocity, like we have with this headland, where you have complicated geometries, you get slightly different inlet velocities which you need to cope with. We're also looking at then power shedding above the rated speed. either by pitch control or variable speed control, either into stall or into overspeed. And you can see here this is a velocity across the bottom, so absolute velocity with power and thrust coefficients vertically on this plot. We start to hit a limiting rotational speed at about 1.2 metres per second for this particular rotor, and we hit peak power at about 1.6 metres per second. And so you can see the curve starting to drop away as we speed limit initially, and then again a more rapid limit as you start to shed power more aggressively. The pitch control does exactly what you want it to do, and you get dropping thrust as you control the pitch, which is what we expect from wind and what we'd like to see here. Anybody that's looked at a wind energy textbook and looked at control strategies, you get plots that look a bit like this. And so here we're running rotor speed horizontally, power vertically. The plot on the left is pitch controlled rotor. So we go to our peak rotor speed and then we start limiting speed, and we go up power, and then we start aggressively going into stall to limit power to 300 watts for this particular rotor. And on the other side we stall control, and in stall control that also brings the speed down once you start pitching heavily away. What that does though, and perhaps this is the point of my talk today, is that control changes the wake. So the wake at the top is at 1.2 metres per second, and we've shown previously that the more energy, the more kinetic energy you have in your flow, the longer your wakes are. But if you start controlling either by pitch control in the centre or stall control at the bottom, you get a very different shape. The isocontour is the 95% isocontour of velocity deficit. So you get different shape wakes in the two conditions. More interestingly, and I don't think we've quite understood the implications of this yet, the turbulence is quite different. So we're actually getting less turbulent at higher speeds with the control strategies. And also the turbulence changes where it is across the rotor as well, and that's partly to do with pitch angles and angles of attack, changing where the turbulence sits from the tip to the centre of the rotor. That's something I don't think we quite understand yet, but interesting work to follow on. So to conclude, both of our modelling approaches are useful for modelling of arrays, and we're going to do some work in the near future looking at the interface and the comparison between how we get those to work more closely together, and we can capture, accurately predict power capture from arrays using these types of models. Thank you.
This production is brought to you by the University of Edinburgh.